My name is Nur Atira Wahida binti Kushaimi with metric number aw200259.
Here I will explain to you guys what is laser Raman spectroscopy. Let's find it out! Raman spectroscopy is an analytical technology used in industry and academic laboratories to understand the structure of molecules and the composition of molecular mixtures in a liquid, slurry, paste, or solid phase. Raman is often compared with IR spectroscopy because both provide information about the structure and properties of molecules from their vibrational transitions. A key difference between Raman and infrared spectroscopy is that Raman is a scattering phenomenon, whereas infrared is an absorption technique. There are two types of scattering, Rayleigh and Raman. Rayleigh is elastic scattered energy, which means the frequency of the scattered photon is the same as the excitation photon frequency. This type of energy is non-informational to the chemical makeup of the molecule being interrogated. Raman scattering, however, is inelastic photon scattering and is highly informational to the chemical makeup.
Also, Raman spectroscopy named after Indian physicist C.V. Raman.
Now let's move on principle of Raman spectroscopy. What is Raman effect and how it can be used in Raman spectroscopy? Firstly, when a sample exposed to a monochromatic light, a visible region sample will be absorb the light like a major portion of the light and get transmitted through the sample. However, a mini part of the light will be scattered by the sample in all directions. One can observe the scattering at a right angle to the incident beam. Hidden light has a particular frequency. If the scattered light has the frequency same as the incident light, then the scattering is called as a Rayleigh scattering. However, it has been observed that about 1% of total scatter intensity occur at frequencies different from the incident frequency, which is called as Raman scattering. Now, what is other technique in vibrational spectroscopy? Want to gain knowledge? Let's go!
So, Raman spectroscopy is one of the branches of the vibrational spectroscopy that focuses on studying the vibrational motions of molecules and materials. It provides valuable information about the chemical structure, bonding, and functional group present in a substance. So here are new knowledge for you guys. In addition to infrared spectroscopy, which is IR, and Raman spectroscopy, there are other techniques used in vibrational spectroscopy to study the vibrational motions of molecules and materials. Some of these techniques include Fourier transform infrared spectroscopy (FTIR), near infrared spectroscopy (NIR), inelastic neutron scattering (INS), terahertz spectroscopy, and also electron energy loss spectroscopy (EELS).
Here we show 5 vibrational modes using carbon dioxide and methane. This model shows the symmetric stretch in carbon dioxide. This is the asymmetric stretch in carbon dioxide, the bend in carbon dioxide, scissoring in methane, and rocking in methane. Infrared spectroscopy.
What can we learn from this energy state? The energy difference between ground state 0 and state 1 depends on only one thing, the natural frequency of the vibration. In the model of spring and balls, when the balls are heavy or the spring soft, the system vibrates in a lower frequency. When the balls are light or the spring is hard, the system vibrates in a higher frequency. The exact same thing happens with molecular vibration. Let's look at two very simple molecules, oxygen and nitrogen. Oxygen has more mass and therefore a lower frequency than nitrogen, and consequently, Raman scattering from oxygen and nitrogen will have a different energy shift. Simple molecules like nitrogen and oxygen have only one vibrational mode. A more complex molecule, such as paracetamol, has 54 normal vibrational modes, and each mode has its own natural frequency. Imagine plucking a harp with 54 strings and capturing the frequency of each string at the same time. Just like this, we get a unique pattern that is very specific for the harp, or more relevant yet, the molecule we are looking at. This is called a spectroscopic fingerprint.
While Raman spectroscopy is not as common as IR spectroscopy, it does provide us with valuable information about molecular symmetry. In Raman spectroscopy, the sample is irradiated with visible light, which the molecules absorb and re-emit. However, some of the energy is absorbed by the molecular vibrations, causing a small portion to re-emit at a different frequency than the incident light. Light can be scattered in two ways: elastically, commonly known as Rayleigh scattering, in which there is no non-kinetic transfer of energy between the molecule and photons, or inelastically, known as Raman scattering. Raman scattering involves the transfer of energy between molecule and photon. Modern Raman spectroscopy instruments are designed to filter out the Rayleigh light because only 1 in every million photons will be Raman scattered.
Assalamualaikum and hi, my name is Nuna Hamidin Musa, code matric aw200250. I will explain to you the basic concepts of Raman spectroscopy. It all begins with a special light source called a laser. This laser emits a powerful beam of light, and this laser beam is directed onto a sample just like a spotlight shining on a stage. When the laser beam meets the molecule in the sample, the light interacts with the molecule, causing a tiny fraction of it to be scattered in different directions. It's like the molecules are sending the signals back to us. This scattered light undergoes a magical transformation known as Raman scattering. During this process, the scattered light interacts with the molecules and they exchange energy, like a dance of particles. This energy exchange leads to a change in the wavelength of the scattered light. This also change in wavelength that's called the Raman shift. It is like a fingerprint that tells us about the vibrational energy levels of the molecules in the sample. Each molecule has its unique vibrational signature, and the Raman shift helps us to uncover their hidden dance. Now it's time to capture and analyze this scattered light. A spectrometer, our trusted detectives, comes into play. It collects the scattered light. The spectrometer carefully analyzes the scattered light, measuring its intensity at different Raman shifts. It's like creating a colorful map that shows us how intense its vibrational dance of the molecule is. Now we go to the applications. In the lab, scientists use laser spectroscopy to study the materials. They shine a laser beam onto a sample and watch how the light interacts with it. Laser spectroscopy also plays a vital role in keeping our environment safe. Environmental scientists use it to measure air quality, detect pollutants, and monitor the levels of harmful gases in the atmosphere. Laser spectroscopy is not just limited to labs and the environment. It has found its ways into hospitals too. Doctors use laser spectroscopy to diagnose disease, examine tissues, and even identify specific biomarkers in our bodies. In the world of industry, laser spectroscopy ensures quality control and safety. It helps manufacture analyze the compositions of material, detect impurities, and ensure that products meet the highest standards. Beyond our planet, astronomers use laser spectroscopy to unravel the mysteries of the universe. By analyzing the light emitted by stars and galaxies, they can determine their chemical compositions, temperature, and even how fast they are moving.
That's all from our group Delta. We very hope that you guys can learn and gain new knowledge from our video, and you guys can share this video if you like. Thank you very much for watching.